Table 430.150 within the National Electrical Code, specifically addressing three-phase motor amperage ratings, saw no changes between the 2002 and 2005 editions of the code. This means that the values listed for full load currents of three-phase motors at various voltage levels remained consistent. To elaborate further, understanding Table 430.150 is critical for electrical engineers, electricians, and anyone involved in motor installations and calculations. The table provides the full load current, or FLA, values for alternating current, or AC, induction motors. These values are used to determine the appropriate conductor size, overcurrent protection, and motor starter size. When working with motor circuits, the NEC mandates using these full load ampacity values, rather than relying solely on the motor nameplate amperage. This is because the table values are standardized and account for variations in motor efficiency and design. Referring to Table 430.150, you'll find amperage ratings for motors operating at common voltage levels such as 208 volts, 230 volts, 460 volts, and 575 volts. These voltages are typical in industrial and commercial settings where three-phase power is utilized. The table is organized by horsepower rating, allowing you to quickly find the corresponding FLA value for a specific motor. For example, a 10 horsepower motor operating at 460 volts will have a specific FLA value listed in the table. This value is then used in subsequent calculations to determine the minimum ampacity of the conductors feeding the motor. When selecting conductors for a motor circuit, NEC section 430.22 typically requires that the conductors have an ampacity of not less than 125% of the motor's full load current, as determined by Table 430.150. This 125% factor accounts for the continuous nature of motor loads and provides a safety margin to prevent overheating of the conductors. Therefore, if the 10 horsepower motor at 460 volts has an FLA of 14 amps from Table 430.150, the conductors must have an ampacity of at least 17.5 amps. The next standard conductor size that meets or exceeds this value would then be selected. Overcurrent protection for motor circuits is addressed in NEC section 430.52. The type of overcurrent protection device, such as a circuit breaker or fuses, and its rating or setting depend on the type of motor, its application, and the specific characteristics of the overcurrent device. Generally, the overcurrent device is intended to protect the motor control apparatus, and the branch circuit conductors against overloads, short circuits, and ground faults. The maximum allowable rating or setting of the overcurrent device is typically expressed as a percentage of the motor's full load current. This percentage varies depending on the type of overcurrent device and the motor's starting characteristics. For example, inverse time circuit breakers are often permitted to have a rating or setting of up to 250% of the motor's FLA. However, the specific requirements of NEC section 430.52 must be carefully followed to ensure adequate protection without nuisance tripping during motor starting. Motor starters, also known as motor controllers, are used to start and stop motors, and they often provide overload protection. The size of the motor starter is determined by the motor's horsepower rating and voltage. Motor starters are available in various sizes, designated by NEMA sizes, such as NEMA size 1, NEMA size 2, and so on. The appropriate NEMA size is selected based on the motor's full load current and the starter's horsepower rating. The starter must be capable of handling the motor's inrush current during starting, as well as providing overload protection to prevent damage to the motor. Overload protection is typically provided by thermal overload relays, which are adjustable to match the motor's FLA. These relays strip the starter if the motor draws excessive current for an extended period, preventing the motor from overheating. In addition to conductor sizing, overcurrent protection, and motor starter selection, Table 430.150 is also used for other motor circuit calculations. For example, it is used to determine the minimum size of disconnecting means, such as safety switches or circuit breakers, that are used to isolate the motor circuit for maintenance or repair. The disconnecting means must have an ampere rating not less than 115% of the motor's full load current, as specified in NEC section 430.110. This ensures that the disconnecting means can safely interrupt the motor's current under normal operating conditions. It is also used to determine the size of control circuit conductors which are used to control the motor starter. The control circuit conductors must have an ampacity sufficient to carry the current of the control circuit devices such as push buttons, relays, and pilot lights. The ampacity of the control circuit conductors is typically determined based on the voltage and current requirements of the control circuit devices. Furthermore, Table 430.150 is essential for calculating the voltage drop in motor circuits. Voltage drop occurs when current flows through a conductor, and the voltage at the load end of the conductor is less than the voltage at the source end. Excessive voltage drop can cause motors to operate inefficiently, overheat, and even fail. To minimize voltage drop, it is important to select conductors with sufficient ampacity and to keep the length of the conductors as short as possible. The NEC recommends limiting voltage drop to a maximum of 5% for motor circuits. By using Table 430.150 to determine the motor's full load current, engineers and electricians can accurately calculate the voltage drop in the motor circuit and select conductors that will maintain the voltage within acceptable limits. In summary, Table 430.150 is a fundamental tool for anyone working with motor circuits. It provides standardized full load current values that are essential for conductor sizing, overcurrent protection, motor starter selection, disconnecting means sizing, control circuit conductor sizing, and voltage drop calculations. While the values in Table 430.150 remained unchanged between the 2002 and 2005 NEC editions, it is always important to consult the latest edition of the NEC and any applicable local codes to ensure compliance. Moreover, it is important to note that Table 430.150 provides values for standard induction motors. For motors with different characteristics, such as synchronous motors or wound rotor motors, different tables or calculations may be required. Always refer to the motor nameplate for specific information about the motor's voltage, current, and horsepower rating. The motor nameplate provides the most accurate and up-to-date information about the motor's operating characteristics. When applying the values in Table 430.150, it is important to consider the motor's service factor. The service factor is a multiplier that indicates the amount of overload that a motor can withstand for a specified period. Motors with a service factor greater than 1.0 can operate at a higher horsepower than their nameplate rating for short periods. However, it is important to note that operating a motor above its nameplate rating can reduce its lifespan and increase the risk of failure. The NEC permits the use of the service factor when calculating the conductor size and overcurrent protection for motors. However, the specific requirements of NEC section 430 must be followed to ensure that the motor is adequately protected. In addition to the service factor, it is also important to consider the motor's temperature rating. The temperature rating indicates the maximum temperature that the motor's insulation can withstand without degradation. Motors are typically rated for Class A, Class B, Class F, or Class H insulation. Each class of insulation has a different maximum temperature rating. When selecting conductors for a motor circuit, it is important to choose conductors with an insulation temperature rating that is equal to or greater than the motor's insulation temperature rating. This will ensure that the conductors can safely handle the heat generated by the motor without overheating. Furthermore, when working with motor control circuits, it is important to understand the different types of motor starters available. The most common types of motor starters include across-the-line starters, reduced voltage starters, and variable frequency drives, or VFDs. Across-the-line starters apply full voltage to the motor terminals during starting. This is the simplest and most economical type of starter, but it can cause a large inrush of current, which can stress the electrical system. Reduced voltage starters reduce the voltage applied to the motor terminals during starting. This reduces the inrush current and minimizes stress on the electrical system. Reduced voltage starters are commonly used for large motors or in applications where the electrical system is sensitive to voltage fluctuations. Variable frequency drives, or VFDs, control the speed of the motor by varying the frequency of the voltage applied to the motor terminals. VFD offer precise speed control and can improve energy efficiency. They are commonly used in applications where the motor speed needs to be adjusted, such as pumps, fans, and conveyors. When selecting a motor starter, it is important to consider the motor's horsepower rating, voltage, and starting characteristics. The starter must be capable of handling the motor's inrush current and providing overload protection. It is also important to consider the application requirements, such as the need for speed control or reduced starting current. In addition to selecting the appropriate motor starter, it is also important to properly install and maintain the motor circuit. Proper installation includes ensuring that all connections are tight and secure, that the conductors are properly supported, and that the motor is properly grounded. Regular maintenance includes inspecting the motor for signs of wear or damage, lubricating the motor bearings, and cleaning the motor windings. Proper installation and maintenance can extend the life of the motor and prevent costly breakdowns. In conclusion, Table 430.150 is an indispensable reference for determining the full load current of three-phase motors. While the values remained consistent between the 2002 and 2005 NEC editions, a thorough understanding of its application, along with adherence to the latest NEC guidelines and consideration of factors like service factor, temperature rating, and appropriate motor starter selection, is crucial for safe and efficient motor operation.